Hello student, welcome to lesson number 6. In this lesson, we are going to look at capacitors and capacitance, but now we concentrate on energy stored in a capacitor. Now when we are charging a capacitor, we remember there is charges that are flowing. The charges are flowing from the battery to where we have the plate of the capacitor. So because there are charges that are flowing, then work has to be done against the repulsion of the negative plate to more electrons flowing in it. And also, work has to be done against the attraction of the positive plate on the electrons flowing out of it. Remember, when you are charging, we have electrons that are coming from the positive plate, and also we have the electrons that are coming on the negative plate. So in these two cases, we have the repulsion due to the like charges, that is the electron, and we have the attraction. So work has to be done to overcome those forces. Now this work done is stored in form of potential energy, and the energy may be converted to heat, light, or other forms, which implies that when you are charging a capacitor, there will be generation of heat or light or other forms of energy, because that work that is being done, that is stored as in form of potential energy, is converted to other forms. So we can say that work done, which is equivalent to the energy stored in a capacitor, is equals to the average charge multiplied by the potential difference. Remember, this is a formula that we know, that work done is equals to QV. But now here we are talking of the average charge. And for you to get the average charge, it will be a half Q then multiplied by V. But we know that V or Q is equals to CV. So by replacing, where we have Q, you replace with CV, you will get that the energy stored will be 1/2 CV squared. Also, remember our V from this one, we can say it is Q over C. So where we have V, we can replace with Q over C. And by so doing, you get that the energy stored will be Q squared over 2C. So it implies that when you are getting the energy of a capacitor, you can either use a half QV or a half CV squared or Q squared over 2C, depending on the values that are given. So a graph of Q against voltage is a straight line through the origin. This one we found when we are charging a capacitor, that the charges increases. As the charges increases, also the voltage increases. And the charges, we found that it is the same as IT, that is current times time. So when you get the current times time and you plot a graph of charge against voltage, it will be a straight line through the origin. From this graph, if you get the gradient, which is change in Q over change in V, you get the capacitance. And the area under the graph represents the energy stored in a capacitors. Because now if you look at this graph, it is a triangle. And for us to get now the triangle, the area of a triangle is a half base times height. That is a half V times Q, which will give us a half QV. So the area under the curve is the energy stored, and the gradient is the capacitance. Then from there, we have the examples. A 4 microfarad capacitor is charged to a potential difference of 80 volts. Find the energy stored. This one, we just use this formula, a half CV squared, because we are given the C capacitance and the potential difference. So substituting the values, it will be 1/2 times 4 times 10 to the power -6. Remember, microfarad or micro is the same as -6, 10 to the power -6, then times 80 volts. You get that the energy stored is 1.6 times 10 to the power -4 joules. Then question number 2. Two capacitors of capacitance, 2 microfarads and 1 microfarad, are connected in parallel. A PD or potential difference of 3 volts is applied across them. Find the energy stored. First of all, we need to get the effective or the combined capacitance. Because they are in parallel, we add 2 microfarads plus 1 microfarad, you get 3 microfarads. So the energy stored will be a half CV squared. So our C now is this one, a half times 3 microfarads times 3 squared, that is our voltage. So you get that the capacity or the energy is 1.35 times 10 to power negative 5 joules. Then we have application of capacitors. Now, a capacitor is used in smoothening circuits. To smoothen, in other words, we are saying that when we are converting an AC circuit into DC, when we talk of an AC, it has the sine curve. But when we talk of a DC, it is a direction, it is a straight line. It is moving from one side or one terminal to the other. So if we are converting AC to DC, you'll find that there are some curves that will be left. So a capacitor is used to smoothen that curve. And that process, we call it rectification. Or rectification is the process of changing or converting AC into DC. So the capacitor is used to smoothen. It's also used in reduction of sparking in induction coil contact. So when we have the induction coil, we place the capacitor so that now it can reduce the sparking by taking up those charges. Then we have the variable capacitor is used in tuning circuit of radio receiver. We have seen that area that you can change the circuit, or you can tune so that you can now change the station of the radio. Then from there, a capacitor are also used in relay circuits that are determined, or they are designed to give intermittent flow of current in car indicators. So they are used in those circuits. From there, we have that they are used in flash, especially when you have a flash camera. They are able to discharge and charge instantly when you are taking photos using that flash. So the light that you get in the flash is due to the discharge of a capacitor. So a capacitor has several uses. You can be able to see this. But now this one depends on the type of a capacitor. From there, we have the assignment. So the assignment is testing what we have just covered. Again, make sure that you are able to recall. And this, for you to recall, you need to practice a lot and maybe discuss with your peers. So thank you, and let us meet in our next lesson.